Good morning, class. This is Mr. Schmidt. We're talking about the answer key. And no one's here. I gotta take this off. This is Mr. Schmidt. We're talking about the answer key to the M3 rotational, inertia, and angular momentum take-home test, which I'd start off with a typo from the very beginning. First, I have two typos. I left this on there, and we're now on 2021. Okay. The first question depicts some accurate information about a pendulum. So this is going to be treated as a point mass, 28 kilograms or 61 pounds at the end of a 67-meter long rope. Okay. So I suppose what would happen if we took that rope and we spread it out 10 degrees past the vertical and started it spinning at such a rate it made one revolution every 5 seconds. Okay. So this is not necessarily a stable situation to get these 2 points together. Okay. But we're going to use the information as it's given. Okay. So first of all, what's the tension on the string? Okay. So in order to find that, we need to know 2 forces. We need to know the centripetal force and we need to know the gravitational force. Okay. So our centripetal acceleration is omega squared times r. Okay. R, we got to use this angle to find that number. Okay. And then we have to find our angular velocity to find this number. Okay. And then second, we're going to plug that angular acceleration in, or centripetal acceleration in, and we get our 2 forces. Okay. Once we have our 2 forces, we can do Pythagorean theorem, and that will give us part A. Okay. Now we can turn back to the question. What is the angular momentum of the bob? So once again, we're treating this like a point mass where we have our mr squared times omega. Okay, this is our m r squared times our angular velocity. Okay, and that gives us our next one. You also see here where I'm awarding points for each skill that you do. Okay, so that was 6 points on that one. Okay, next up, we have the largest wind turbine under construction. Another true fact here I pulled from the internet. Okay, we have 107-meter long blades that are going to act like a rod. Okay, and we have the mass of each blade. Okay, and then I suppose what would happen at this speed, which is an achievable speed for most wind turbines. Okay, so what is the linear velocity of the outer end of the rotor? Okay, so we know the radius of each blade, the mass of each blade, the angular velocity of the blade. We can get that into radians per second. If we have it in radians per second times the radius, okay, that gives us our linear velocity. Okay, next up, what is the centripetal acceleration? Okay, so we can do that one of 2 ways. You could do it just like the last question, or you could use this fact and use linear velocity divided by r. Okay, either way it should approach the same number. Okay, and moving on here. What is the moment of inertia for each individual blade, which here I say specifically are acting as a rod. Okay, so we need the equation for the inertia of a rod. Okay, so that's 1/3 mr squared. So we get that. It's a very big number. Okay, this is one of those moments. Some of you did your significant figures. All right, we only have these out to about 3 digits here. That's about out to 5 digits, 2 digits. Okay, if you express more than 5 digits of certainty here, you're not really accurately representing the calculation. Okay, so please keep that in mind as you go through those. All right. Next up, I had some fun trying to find something that would have 2 turning objects. And what I stumbled upon was this picture of 2 ice skaters. So way this, what's called a death spiral happens is the two people start, okay, Marissa here has an approach that is circular. She then links arms with Mervyn, and her angular momentum joins with his angular momentum, and they end up spinning. Okay, so a couple points here. So we say Marissa's point mass is, Marissa is acting like a point mass. I was thinking about if we could make this a rod, but the rod doesn't extend all the way to the center, which would be an even more complicated equation, and I didn't want to introduce a type of object we haven't seen before of a disconnected rod. Okay, and then I said Tran was a solid sphere as another object for you to prove you knew all the different equations here. Okay, and we're trying to find the common angular, and here's my other typo here. Hang on, everybody got the context. I wanted velocity and radians per second. All right, so let's take a look now at, oops, no, that's that one. Okay, so we have two people here. Marissa with a point mass, okay, and Marvin Tran with the spherical equations, okay? So one important thing is she changes her radius. That's the whole impetus of this change. And then they link arms, and that causes a new change. So we need the momentums to be conserved. So her initial momentum and her final momentum, his initial momentum, his final momentum, okay? Notice he was not spinning beforehand. He had a, so he had his toe pick set, so he was kind of relatively stationary for a moment when they linked up, okay? And so we have to go through the different ones, okay? What is his inertia? Okay, what is her initial inertia and what is her final inertia? Okay, notice she changed her radius, which changes those numbers. Okay, all right, so from there, we can then plug in our numbers and we solve. Okay. All right, now let's move on to the last one. This one, it was nice to see a lot of people did very well. If we think back to September and October, I think you all would have very much struggled with this, but now you perceive this as the easy question, and saw a lot of points rack up here. So I'll just go through. We're trying to find angular acceleration, okay, angular displacement, torque, and then work, okay? And what we're going to see is there's going to be lots of ways to approach these questions, and they'll all generate the same answer. Okay, so we know it starts at rest and then it spins. By the way, this object that we're talking about, this is used for a lot of different fluids, especially in like lab tests for humans, so blood, plasma, those types of things. If it spins fast enough, the heavy objects are forced to the bottom very quickly, and the lighter fluids or lighter objects remain at the top. And so you can separate out different fluids very quickly and test for or extract plasma or do other types of parts within a cell that are extracted from your sample. So it's spinning really fast. We spin it for 20 seconds, okay? So we have our angular acceleration as our change in velocity over change in time, okay? We saw a lot of success on this one. Second one, you could solve either way here. Now we know our velocities, we know our acceleration, we know our time, okay? So you have some choices. Either way, you should get the same answer, okay? Next up, what are we trying to find here? We're trying to find the torque. So we need to know the inertia and the acceleration. So the flywheel is a disk, okay? That's probably one of the biggest facts you need to pull from that. Okay, so then we're going to use the disk equation, and that'll give us our inertia, okay? And then we plug everything in, And we got our answer. All right. Next up, so here, remember, we saw two different ways to solve for the equation. Here, there are also two ways to solve for the equation. Okay, you can do the torque times the change in the displacement in the angle, or you can do the change in kinetic energy. Okay. Ironically, I forgot to type in my 1/2 when I first did this. Okay, and I was looking at everyone's answers. I'm like, why is your work so good and your answer is different than mine? And the answer is I had a calculator mistake. Okay, so as always, make sure you square your number, make sure you multiply by 0.5. Okay, and that should give you your answer, regardless of which way you solved it. All right. All right. So yeah, that answers the questions. And I will see you all in class and have a good day.